Okay, so with these notes, we're going to be looking at section 1.6, and it's just a variety of different types of equations. We're also breaking this section up into two sets of notes. So the homework for this part will be homework 1.6.1, and then we'll have another part, 1.6.2. Okay, so let's get started. We have rational equations. So rational, you can see, of course, the word ratio in there. So we have expressions both on the top and the bottom of fractions, right? So, and it's in the form of an equations. Now, we dealt with things like this before when we had rational expressions. So we had something maybe just like these two fractions would be added together. And we'd get a common denominator, turn them both into that common denominator by multiplying the top and bottom so that we would get the same denominator. And then we would just simplify, and then if we could cancel stuff, we did. All right, but now we've got an equation. And so the process is similar but different. So what we first want to do is, well, first let's talk about what the domain is. All right, so what's the domain here? And so instead of talking about what values x might take on, at this point we want to talk about what values could x not take on. And so really what we want to think about is what would we have to eliminate if it came up as a solution. So, we work through the problem, we have x equals, and we get some number, and what number would be bad? What answer we know would make this equation not exist, right? Or, and in this case, because it's just rationals, we don't want a denominator to take on a value of 0. So what x value would make this, no x value would make this denominator 0. That denominator is 2. So it doesn't matter what x is, it's still going to be 2. So that's not going to cause a problem. But here, we could potentially have x plus 1 equals 0 if x were equal to -1. And so what we say is, instead of saying what values x can take on, because we don't know what the solution is, but we can say what we know it can't be. And so x would not be able to be equal to -1. And so if that shows up as our solution, or maybe we have more than one solution, but if that shows up as one of our solutions, then we would eliminate it, because that would make the original equation undefined. Okay, so now the process that we go through is a little different. We still look for the least common denominator. So the least common denominator here is, well, there's a 2 in it, and there's also an x plus 1 in it. Okay, now what we do with it is different now. We don't turn the denominators into the LCD. Because it's an equation, we can interact with this a little differently than we could if it was just an expression. So what we're going to do is we're going to multiply each part. So we're going to multiply this, we're going to multiply this, and we're going to multiply this by the LCD, and we'll cancel it, right? So I'm going to write it all out this first time, but then the rest of this is kind of the canceling process I'm going to do in my head. But this first time, I'll do it. So we're going to multiply 2, x plus 1, 2x minus 3, that was there, over 2, plus, we're going to multiply 2, we're going to do, we're going to multiply by x plus 1, 2x plus 1, times the 5x that's there, and then that's over x plus 1, and then, let me just get that a little bit out of our way. And so then I'm going to multiply this last part on the right-hand side also by the same thing, 2, and then x plus 1. Okay, so what I've done is I've multiplied. And when I multiply, I don't multiply top and bottom by it. I just multiply the tops by it, by the LCD. Okay, and so what happens is that will cancel with that. And this x plus 1 will cancel with this x plus 1. So we've turned all the denominators into 1, and we made the equation much simpler. All right, and so that's the whole key here. We don't turn the denominators into the LCD. Instead, we multiply everything by the LCD and we cancel it. Now, I normally don't write out this step. I think in my head, again, let's rewrite it up here out of the way. LCD was 2 and then times x plus 1. And so I multiply in my head these things and I say, oh, okay, the 2's cancel. What's left? Just the x plus 1. So really what I write is x plus 1 was the thing that didn't cancel, and that's times the x minus 3. And then the x plus 1 is what canceled, leaving us with 2 times the 5x. And then this nothing canceled because there wasn't anything in that denominator. This denominator was just 1, so nothing canceled. And so let's go ahead and start simplifying that a little bit. 2x and then x plus 1. Okay. So I generally don't write this line. I do that in my head, but I wanted to show what was going on so that you can do it in your head and do this. Okay. All right, so now we just want to simplify and see what kind of equation we have. Like we'll probably have a quadratic because I can see I have an 2x times an x here. So we're going to probably have an x squared. Looks like we're going to have an x squared over here. Let's see what happens. All right, so let's FOIL this out. That is going to be 2x squared. We have negative 3x and a 2x, so that's going to be negative x and also minus 3. This will be plus 10x. And here we have 2x squared plus 2x. All right, and now we really just want to simplify this. Now, it looks like we have a quadratic. However, it looks like that's going to cancel with this. So it looks like we're just going to have a linear equation. Let's bring, I don't know, I'm thinking, all right, let's take everything to the left because this is 9x. And then we're going to subtract 2x, so that's going to be what, 7x? And then what is that? 7x minus 3, and that's equal to 0. All right, and then we want to just solve that. It's a simple linear equation in this case. And so take the 3 to the other side, divide by 7. That's going to be x equals positive 3/7. And that is our solution. All right. All right, so the next one, B. So on this one, it's obvious what the LCD is. I'll go ahead and write it out. There's only, this has no denominator or a denominator of 1, really. And then so we have x minus 5, x minus 5. So clearly, x minus 5 is the LCD. All right, so now multiply through the tops by the LCD. And again, if you can skip this step and do this part in your head and just write down this step, that would be good. Save yourself some time and some space on your paper. All right, so when I multiply this x by the x minus 5, the x minus 5 is going to be canceled. And so that's really just going to leave me x. And then the 5 gets multiplied by this, it doesn't cancel, so that's x minus 5. And then when I multiply this 5 by the LCD, it's going to cancel, leaving us with just 5. All right, so we want to solve this equation. This one's pretty easy. We're going to have what? That's going to be 5x, that's going to be 6x. Distribute that, that's going to be negative 25 equals 5. And then, of course, we can bring the 5 over. And so that's going to be 6x minus 30 equals 0. In actuality, it would have been smarter to take the 25 to the other side. But I was kind of setting it equal to 0 like we kind of do. And then move this over, divide. So x is equal to 5. Now, the problem with that answer is we didn't really think about it, but what x value would make this undefined. And so we know as part of our our domain, x cannot equal 5. And so this is not a valid answer. All right, so don't box that in and move on. That would be wrong. So we have no solution. So we put in a little null set, or you could do an empty set, or you just write out no solution. Okay. So this one gave us sort of a pseudo answer, but that answer does not work in the problem. Okay, moving on. Next one, we want to find the LCD again. And probably we want to factor this. So this will be x plus 5 and x minus 5. All right, pause the video and do this problem and see how you do. We know the LCD is the binomial x plus 5 times x minus 5. Okay, so when I multiply this LCD by the x plus 5 is canceling. That leaves me with just x times x minus 5. When I multiply this 5 by the LCD, the x minus 5's cancel. That leaves me with 5 times x plus 5. And when I multiply 50 by the LCD, everything cancels that I multiplied. And so that just leaves me with 50. All right, and so now, again, if you needed to write that intermediate step, write it all out and then cancel it, that's fine if you're having problems doing this in your head, but probably just saves you some time if you can get in the habit of doing that. All right, so we have x squared minus 5x plus 5x plus 25 equals 50. This is definitely a quadratic equation. So you'll notice the 5x's cancel, the negative 5x and the positive 5x. And then what we'll do is we'll bring the 50 over. Well, in this case, no, we don't want to set it equal to 0. Let's move the 25 over. So we get x squared, because the middle term's missing, so we don't want to really set this one equal to 0. 25 equals, x squared equals 25. And so x is equal to plus or minus 5 when we take the square root of both sides. However, those two answers, no good. So again, in this case, we have no solution, because the two answers we got do not work. The two answers make the original equation undefined. Okay, next one. Go ahead, pause the video, work on this one, and then unpause the video. All right, I'm going to go ahead and factor this part, this denominator. And so I think you can see pretty clearly the LCD is x times x minus 3. And when I multiply this by that, the x minus 3 cancels. So that's going to leave the x times the x minus 5. The x will cancel this time, leaving me with 1 plus x minus 3. And then on this last part, the whole denominator goes away, cancels everything up there. That's leaving us with just negative 7. Okay, when we distribute, we get x squared minus 5x, just plus x minus 3 equals negative 7. This one's definitely a quadratic. We want to combine like terms and bring things over. We end up with x squared minus 4x, plus 4 equals 0. All right, and that's it's a perfect square trinomial, and so that would just factor into x plus minus 2 equals 0. And so we get a squared, quantity squared, and then so x is equal to just 2. So this is one of those, one of these repeated roots, right? So we get one answer, but it's kind of like a repeated root. All right. So is that one okay? Yeah. I mean, what would we have to eliminate if it showed up? X equals 0 couldn't be an answer, and x equals 3 could not be an answer. So that would be sort of our domain, but 2 is not in there, so we're good. Okay, so we had one solution in that case, x equals 2. All right, so we want to talk about job rate things. And let me just kind of do a little sidebar for a second. So, and this is like rate at which you can do jobs and things. So let's say that Bob takes 10 minutes to wash a car and Sue takes 12 minutes to wash a car. Okay, so we could say that in an hour, Bob can wash 6 cars an hour. So we could think of that as his rate, right? And Sue can wash 5 cars in an hour. So if they're working together, then we know that they can wash 11 cars per hour, right? That makes sense. 11 cars per hour, because if they're working together. So that's kind of what we want to talk about is combining rates. It wouldn't make sense if we went up here and we said, well, he can do it in 10 minutes, she can do it in 12 minutes. Together, it takes, it's not going to be that it takes 22 minutes to wash a car, right? That doesn't make any sense. So you have to be careful when you combine things. That doesn't make sense. He can wash a car in 10 minutes, she can wash a car in 12 minutes. If they work together, it's not, you don't add up that, right? So you don't add up the times. What we do is we add up the rates. And so, of course, 10 car every 10 minutes is the same as 6 cars an hour. So that's a rate. So we just have to make sure that we are adding, when we're combining these things, that we're adding the rates at which they work, not the time required to do the work, right? Does that make sense? Okay, so just kind of a little sidebar there. All right, so work rate problems. If a job, say raking leaves, can be done in 3 hours, then the rate is 1 job for every 3 hours. So you don't want to think about this job being 3 hours. You want to think of it as 1 job in 3 hours. Like we often won't say that. We'll say, oh yeah, it took me 3 hours to do this job. So we'll say hours per job, but we really want to say the jobs per hour. And if we're going to add things up, okay? And it would be the same as like saying not how many minutes per car, because we can't add that up. That wouldn't be 22 minutes, okay? So we have to think of it as number of jobs per number of hours, or whatever the time unit is. We could say 1/3 of a job per hour if we wanted to as well, okay? So if if the job takes t hours, then we think of the job rate R as 1 divided by t. And then if we want to know how much work was accomplished in total, we'll call that A. Then that would be the rate at which the job is being done times how long you spent doing it, T. Okay, so let's look at example A. If Mercedes washes 6 cars per hour and George washes 5 cars per hour, okay, this sounds a lot like what I was just doing, right? How many cars can they wash working together per hour? So obviously the answer here is 11, like my little sidebar. But let's make sure that we are doing this in terms of rates, because we're adding up the rates. So it's 5 cars per 1 hour plus 6 cars if we start with Mercedes. So 6 cars and then 5 cars for Jorge. So 5 cars per 1 hour for Jorge, and together they can obviously wash 11 cars per hour. Okay, so again, you want to think of it as not cars, or because it doesn't always work when you look at how many things. It depends on how many things per hour. So you want to make the units the same. If I knew that Jorge did 5 cars in 2 hours, then I would have to add up, get common denominators and that kind of thing too. Okay, so it's not just as simple as adding up the number of cars they can wash, because we have to take into consideration how long it takes them to do that, or look at the rate. Okay, so that's an overly maybe simplified problem, and I'm making it complicated, but you really want to think of it as the rates that we're adding up. All right, Lisa and Keith are raking leaves in the backyard. Working alone, Lisa can rake the leaves in 5 hours, and Keith can rake them in 4 hours. How long would it take them to rake the leaves together? So, you know that it can't be that it would take them 9 hours, right? We don't add up the hours. So you have to be careful. Let's make a rate. So let's look at the rate together. So, well, individually, and then we'll add them up. So let's see, Lisa rakes leaves in 5 hours. So she can do one job, which is raking the backyard, in 5 hours. So again, we're doing this as a rate. And then Keith can rake them in 4 hours. So he can do that one job, raking the backyard, in 4 hours. All right, so we want to add these up. Of course, we're going to have to get common denominators, multiply top and bottom by 4. So she could do 4 jobs in 20 hours, and Keith could do 5 jobs in 20 hours. And so their rate together is, well, they could do 9 rakings of the backyard in 20 hours. Okay, so I mean, there's not 9 backyards to rake. Obviously, they just have one backyard, but that is their rate. They could do together. They could do 9 jobs in 20 hours. And so now what we want to do is say, okay, so how long would it take them to rake the leaves together? So let's look at our rate. A equals RT. Now we know the rate, right? So we know that the total amount we want them to do is just their backyard, right? So it's one job, I guess if you want to say one job or one backyard, whatever you want to say, is equal to the rate, which is 9 jobs in 20 hours. And it's kind of good to keep your units here. And then T, we want to solve for T, right? So how long would it take them to do that if they worked together? So we just want to solve that one for T, and it's pretty simple. So we really just want to flip that. So we have one job. Again, you can kind of get rid of that, but one job, and then we're going to flip this thing. So we have 20 hours in 9 jobs. All right. And so, of course, now I know the jobs are going to cancel. It's good to keep your units in here. And then, so that's equal to T. And so if you calculate that, you get something like 2.2 repeating hours. It asks us to do it in hours and minutes. So, how do you do this? So in your calculator, you have you currently have, let me just put this in my calculator. We had 20 divided by 9. And so we have, 2.222 repeating. And so how do I do that? So I'm going to take away the 2. So I know it's 2 hours. And then how many minutes is that? So I'm going to take my 2.222. I'm going to subtract 2 from it, and that just gives me the decimal part. And now what I'm going to do is I'll multiply that. That is hours. And I'm going to multiply that by 60. All right, and so that's 13.33. So let's just say, rounding to the nearest minute, that would be 2 hours and 13 minutes. Okay, if you wanted to do hours. So we simply subtract away the 2. We know that's 2 hours. And we take the decimal part of the hours and multiply by 60. Okay. All right, so we have one more problem to work on here on the next page. Let's move over to that page. And so it's another work problem. sometimes a little table will be helpful in a little table will be helpful in evaluating the problem. Okay. So let's read this. So one printer can do a job twice as fast as another. Working together, they can do the job in 2 hours. How long would it take each printer to do the job itself? So if you can pause the video and try to work on that a little bit and see what you can do with it. All right, so I'm going to use each row for a different printer. So I'm going to just label this one the slow printer and this one the fast printer. Okay, and so the slow printer, that's printer A, right? One printer can do, I'm just going to call it printer A. It doesn't really say how long will it take. It doesn't really label them, so let's just call this printer A to differentiate between the two. So printer A, we'll call this one printer B. Okay. So one can do it twice as fast as the other. So how long would it take for each printer to do the job by itself? But working together, they can do it in 2 hours. So let's think about each one is working continuously for 2 hours. So the time, that's going to be 2 hours for each one. Okay? And so if you think about printer A, that's the slow one. Let's assume its rate is 1 job per X hours. So the rate at which that printer works is it can do 1 job in so many hours. Okay, the number of hours being the variable. All right, so then if that's true, what would the rate be for printer B? So printer B, again, is the faster one. So remember that one printer can do the job twice as fast as another. So instead of cutting the hours in half for that one, let's just double the job. So 2 jobs in the same X hours. Whatever that hours is, it can do 2 jobs in that set hour. Okay. And now what we can do is sort of multiply across, right? So this is like the rate times time equals amount of work done. This is the amount of work done, but by each printer. And then, of course, we can add up the work done for each one is the total amount of work done. All right, so this will be 2 over X, and this one will be 4 over X. And probably be good to say, that's going to be what? This is hours, and this is hours. So when I multiply these two things together, this unit is just jobs, right? And then this unit is just job, right? So this is the part of A, the total amount work done by the slow printer, and this is the amount work done by the fast printer. So we have 2 over X plus 4 over X, and that's got to be equal to the total amount work done, which is just 1 job, right? So it's a big, long job. Working together, they do the 1 job in 2 hours. So we know it's 1 job, so now we just need to solve this for X. You can see why we're doing these types of problems in this section, because this again is a rational equation. Okay, so what we do here is we multiply through by X, so we get 2 plus 4 equals X. So the LCD here was X, and so when I multiply by X, the X is canceled, leaving us with 2, and same thing here. Okay, and so that means 6 is equal to X. And then you just got to be careful. You can't just say, oh, there's my answer, and move on. You want to make sure you answer the question. How long would it take for each printer to do the job by itself? So let's talk about the slow printer. And so we know that is 1 job in 6 hours, right? We look at the rate. So how long would it take to do the job by itself? Well, that's one job in 6 hours. So the slow printer, that would be 6 hours for it to do the job. And then the faster printer, it is 2 jobs in, again, 6 hours. And so I think you can see that that would result in taking 3 hours per job, right? And really we want to almost think about how much time per job, so we've almost just flipped this and reduce it. We didn't really think about that here, but we kind of flipped this and said how many hours per job, because that's what they're asking. So it's still a rate, but it's the hours per job rather than jobs per hour. Okay? All right, so the homework for this first part of section 1.6 is here. Remember multiples of 3, so 18, 21, 24, all the way up to 36. Okay, and then the odds for this last part.